Everyone, welcome to topic 4.3, representation of reactions. In this, you will be able to represent a given chemical reaction or physical process with a consistent particulate model. Feel free to jump to the I do, we do's if you have read through these already. So there are many pieces of information that are conveyed in a chemical reaction. For instance, on the left side are reactants, right side are products or things made in the reaction. The arrow indicates that you are yielding something. Coefficients help us to maintain mass balance so that the law of conservation of mass is properly represented. We have physical states. Subscripts help us identify compounds, and then those contribute to the formula units. Chemists often create particulate models as well to represent reactions on a molecular level as a way to visualize changes that take place as atoms rearrange. So here we have a visual of what's going on at the molecular level or particulate model for the reaction that we started with. So some important key parts of a representation: make sure that you're paying attention to the relative location. This includes the phase or state of matter, and that you are representing solids, liquids, or gases appropriately, and that in aqueous solutions, you need to only show the solute particles, including charge for ions. The only time you should show water is if you are talking about intermolecular forces and you need to make sure you're orienting the dipoles, and the computer screen's dirty, so woo. Okay, so pay attention to how they're being organized, that solids have a regular pattern, liquids are close together but no pattern, and gases are far apart. You should also watch for some context clues, including surfaces of alloys or solids as well, precipitate formation, that they should be settled at the bottom, and then interfaces were two different substances. Also, you should pay attention to the amount of the substance you have. This should be total amounts as well as concentrations, and that you're keeping ratios the same if you are given a chemical formula. And make sure you are paying attention to the law of conservation of mass as well. Making sure your species in your models are different, so you can use distinct shapes, symbols, colors, or shades to identify different species. Show charges when necessary. You can use a key to do that as well, as long as it is very clear what you are doing. And also make sure you are trying to use appropriate sizing where applicable. Sometimes it's hard, but try as best as you are able, especially if you're talking about ions, that the lithium ion should be significantly smaller than maybe an iodine ion. Okay, so now we're going to look at the I do's. The pictures below show the process of a reaction as hydrogen gas and bromine gas react. This reaction doesn't go to completion, rather it reaches a state of equilibrium. Equilibrium means that the forward and reverse reactions, that there is a reverse reaction that happens, but once it hits equilibrium, those two rates are balanced and the reaction appears to stop. But you still have some reactants that are unreacted. So the formulas for the reactants in picture 1 are given to us actually, and that is just hydrogen gas and bromine gas. You can use the key that is given as well to determine that. The product formula, which would be in pictures 4 and 5, we see we have something new that is made, and that has a dark circle and a white circle. So that would be one hydrogen atom and one bromine atom, so HBr. The balance equation for the reaction, if we were to do this, we start with picture 1, which has just reactants, so that's hydrogen, and that is a gas, because they are all separated and spread out, plus bromine gas, and it is all separated and spread out, so that is a homogeneous mixture up there. Woot woot. And then it's going to yield our product, which we looked at in part 2, and that should be HBr. And if we see them, they're all spread out, so that is probably a gas as well, because they aren't touching and there is a random arrangement. When we balance this, we notice that we need to write a coefficient in front of the product, so that way we have 2 hydrogen atoms and 2 bromine atoms on both sides. To add in, since this is an equilibrium reaction, We usually use half arrows that indicate that the reaction proceeds in both directions. Looking at the difference between picture 2 and picture 3, the main difference between these two is that more products are formed in picture 3, so it is further along in the reaction. So our next question is, what do you notice about the total atoms of each element in all of the pictures? What concept does this represent? So if we look back at our pictures, we see we have in each picture 8 atoms of hydrogen and 8 atoms of bromine. This tells us that the total number of atoms do not change. So this supports and follows the law of conservation of mass. So mass is conserved. Okay, now let's look at our we do. So you are going to draw the representation of 4 molecules of hydrogen and 4 molecules of oxygen completely reacting to form water. It gives you a hint that these are molecules, so that means we are talking about the diatomic elements, H2 and O2. So you're going to have 4 sets of each of these. That means that you're going to have 8 total. So it will help if you first write a balanced chemical equation. And we are making water, so H2O. Now we need to balance it, so 2 here, so that we have 2 oxygen, but that also means that we now need 2 hydrogen molecules. So this is balanced, so this is going to tell us the ratio in which our reaction occurs. So you need a key, so we will follow along with what was before, that or make your own, that this is oxygen and this one's hydrogen. And so in the beginning it says we have 4 hydrogens, which are our open circle, and then 4 molecules of oxygen, which are going to be our closed circle. So you're going to draw your model that way. And then keeping the ratio from the balanced reaction we wrote, you are going to draw the products. Please pause the video and complete your products now. That you make 4 molecules of water. So the ratio should be for every 2 hydrogen molecules, I make 2 water molecules. So for every 4 molecules of hydrogen, we make 4 molecules of water. But that also means that we have 4 atoms or 2 molecules of O2 left over that are unused. Okay, and if we count, we see that we have 1, 2, 3, 4, 5, 6, 7, 8 hydrogen atoms, and 1, 2, 3, 4, 5, 6, 7, 8 oxygen atoms. So mass is conserved, but we can only react until we run out of one reactant, because that is limiting. Thank you for tuning in. Please complete the you-dos on the following page here and check your work as you go.